a commercial building, the primary and secondary grounding electrodes play crucial roles in ensuring electrical safety. The primary grounding electrode is typically the cold water piping that extends at least 10 feet into the earth, connecting to the city main. This provides a direct and low resistance path to ground, essential for dissipating fault currents and lightning strikes. The secondary grounding electrode serves as a backup, providing an alternative path to ground in case the primary electrode is compromised. Examples of secondary grounding electrodes include building steel and ground rods driven through the slab into the earth. The National Electrical Code (NEC) provides guidelines for grounding systems, but it does not explicitly list building steel as an approved primary or secondary grounding electrode. However, the NEC does allow for the use of other electrodes as specified by the authority having jurisdiction. Local codes may permit the use of building steel as a primary or secondary grounding electrode, provided it meets specific criteria. Firstly, the building steel must be made of steel or other ferrous metal that is at least 1/4 inch thick. Secondly, it needs to be continuous and electrically connected throughout its entire length to ensure a reliable grounding path. Thirdly, the steel should not be isolated from the earth by paint, rust, or other non-conductive coatings that could impede its ability to conduct electricity. If building steel is used as a grounding electrode, it is crucial to bond it to the cold water piping to create a comprehensive grounding system. This bonding can be achieved by tapping off the steel on one side of the building and connecting it to the cold water piping on the other side, ensuring electrical continuity. All grounding electrodes must be connected together to form a complete grounding system. This interconnection ensures that all available grounding paths are utilized, enhancing the overall effectiveness of the grounding system. The primary grounding electrode is considered the most important part of the grounding system, as it provides the primary path for fault currents and lightning strikes to dissipate safely into the earth. The secondary grounding electrode acts as a backup, ensuring that a grounding path is still available even if the primary electrode is damaged or disconnected. When installing grounding electrodes, it is essential to follow all applicable codes and regulations, including the NEC and local electrical codes. Proper grounding is critical for protecting people and equipment from electrical hazards. The grounding electrode conductor (GEC) connects the grounding electrode to the electrical system's grounded conductor, typically the neutral bus in the service panel. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC must be sized to handle the maximum fault current that could flow through it. Ground rods are commonly used as grounding electrodes, and they must meet specific requirements outlined in the NEC. Ground rods must be at least 8 feet long and have a minimum diameter, typically 5/8 inch for steel or 1/2 inch for copper. Ground rods should be driven into the earth to their full length, and they should be spaced at least 6 feet apart if multiple rods are used. The NEC also specifies requirements for the resistance to ground of grounding electrodes. Ideally, the resistance to ground should be 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. The purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing the overcurrent protective devices such as circuit breakers or fuses to quickly trip and clear the fault. Without proper grounding, fault currents could flow through unintended paths, such as building steel or equipment enclosures, creating a shock hazard. Grounding also helps to stabilize voltage during normal operation, reducing the risk of voltage fluctuations and transient voltages. These voltage fluctuations and transient voltages can damage sensitive electronic equipment. In addition to grounding electrodes, bonding is also an important part of the grounding system. Bonding involves connecting all metal parts of the electrical system and any other metal objects that could become energized to the grounding system. This includes metal conduits, equipment enclosures, and metal water pipes. Bonding helps to create an equipotential plane, which minimizes the voltage difference between different metal objects, reducing the risk of electric shock. The NEC specifies requirements for bonding conductors, including their size and installation methods. Bonding conductors must be sized according to NEC Table 250.102, and they must be installed in a manner that provides a lower impedance path for fault current. Proper grounding and bonding are essential for ensuring electrical safety and protecting people and equipment from electrical hazards. It is important to consult with a qualified electrician to ensure that the grounding system is installed correctly and meets all applicable codes and regulations. In addition to the NEC, other standards and guidelines may apply to grounding systems depending on the specific application. For example, IEEE Standard 142, also known as the Green Book, provides recommended practices for grounding and bonding of electrical equipment in industrial and commercial power systems. It's important to understand the difference between grounding and bonding. Grounding connects the electrical system to the earth, while bonding connects metal parts together to create an equipotential plane. Both grounding and bonding are necessary for a complete and effective grounding system. The grounding electrode system should be inspected and tested periodically to ensure that it is functioning properly. The resistance to ground should be measured to verify that it is within acceptable limits. Any damaged or corroded grounding electrodes or bonding conductors should be replaced. Proper grounding and bonding are not only important for safety but also for the reliable operation of electrical equipment. A well-designed and properly installed grounding system can help to prevent equipment damage and downtime. When working with electrical systems, it is important to always follow safe work practices. Wear appropriate personal protective equipment such as safety glasses and gloves, and energize circuits before working on them whenever possible. Never work on electrical equipment unless you are qualified to do so. If you are not sure how to do something, consult with a qualified electrician. Electrical safety is everyone's responsibility. By following safe work practices and ensuring that electrical systems are properly grounded and bonded, you can help to prevent electrical accidents and injuries. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or engineer for specific recommendations regarding your electrical system. Grounding systems are complex and require careful design and installation. It is important to understand the principles of grounding and bonding and to follow all applicable codes and regulations. By doing so, you can help to ensure the safety and reliability of your electrical system. Always remember to prioritize safety when working with electricity. A well-maintained grounding system is a critical component of any electrical installation, providing a safe path for fault currents and protecting against electrical shock hazards. In summary, the primary grounding electrode, often the metallic water pipe, provides the initial low-resistance path to earth. The secondary grounding electrode, which could be building steel or ground rods, supplements this path. Proper bonding of all metallic components ensures an equipotential plane, minimizing shock hazards. Adherence to the NEC and local codes is paramount for a safe and effective grounding system.